Welcome back, Chem 121. We are going to continue our lecture, which is going to be on the rest of Module 1. And we're going to begin that lecture looking at significant figures, which is where we left off from the lecture previous to this. All right, significant figures are important when we make measurements. All measurements contain uncertainty. The uncertainty in a measurement is going to depend on the instrument that's used to make the measurement. A digit that must be estimated is called uncertain and is usually the last recorded digit. This slide shows you two different balances. This balance can be reported till 2 digits after the decimal place, which means this is the uncertainty. The uncertainty in this measurement is plus or minus 0.01 grams. So if I made a measurement, and let's say I got 2.56 grams, my measurement would really be between 2.55 and 2.57 grams. So plus or minus 0.01 grams. So this indicates how certain I am of the measurement and where my uncertainty lies. This balance over here actually has a much greater certainty because I have 4 digits after the decimal place. So if I made that same measurement, let's say I get 2.5631, what I know is my measurement is between 2.5630 to 2.5632, right? That is going to be plus or minus 0.001. So this is much more certain of a measurement. Now, this device is a lot more expensive and is built to be able to give me a lot more precision and a lot less uncertainty. You would see both of these in a lab. Sometimes we don't need to be that precise, so we might use this less expensive balance. Sometimes we need to have a lot of certainty, and then we're going to be using the more expensive balance. The significant figures that I report in a measurement are reflecting precision. The precision of a measurement is going to depend on the instrument that is used to make the measurement. This is a more precise measurement because with that degree of uncertainty, the measurements that I make with that instrument are going to be closer together than with the type of uncertainty I have in that measurement. When I do calculations, I want to always be conscious of the fact that I need to preserve this precision that is inherent in making these measurements. So we're going to start looking at rules that can be used to use significant figures in calculation. So let's start at the beginning. What is a significant figure? A significant figure is the total number of digits recorded for a measurement. Generally, the last digit is the digit that is estimated or uncertain. So if I were going to look at my examples here, this is the uncertain digit. Here, this is the uncertain digit. Again, it's a reflection of the precision in that particular instrument. With the balance actually does the estimation. If we have something like a graduated cylinder or a ruler, we have to make that estimation based on the gradients that are present in whatever device we're using. Not all numbers are measured numbers. There are also exact numbers and relationships. I know that there's 7 days in a week, and that's a certainty. I know that there are 30 students in a class, or I have $10 in my bank account. When it's a certain thing, like an exact number, which is counting, or a relationship, which is more of a definition, 1 week equals 7 days, right? These numbers are said to have an infinite number of significant figures, which basically means that they don't count when I use my rules and calculations for significant figures. They're not going to be used in order to figure out how many significant figures I report in my calculated number. So the greater the number of significant figures, the greater the certainty. Remember, if I had my balance that was plus or minus 0.1 grams versus plus or minus 0.0001, this measurement is much more certain than this one. So to determine the number of significant figures in a number, or what I report when I make a measurement in the lab, I'm going to follow a couple of basic rules. First of all non-zero digits are significant. Any number that's not a zero is counted as a significant figure. Interior digits, these are also called captive digits. These are zeros between two non-zero digits. These are always significant. So here, that 0 is between the 4 and the 8, so that 0 is a significant figure. Both of these pink zeros are between non-zero digits, so they're all significant as well. Now, leading zeros, the zeros that lead up to the first number in the measurement, the zeros to the left of the first non-zero digit, these are not significant. They only serve to locate the decimal point. So these are more like placeholders. They just tell me that this measurement starts at 3/1000th of whatever unit it is. Trailing zeros, zeros at the end of the number, are more difficult. They may or may not be significant depending on what type of zero they are. If they're after a decimal point, they're always significant. This is telling me that my precision is plus or minus 0.001. If I just reported that as 45, my precision would be plus or minus 1. This is much more certain than this. So this number is much more precise than that. If I use that really expensive balance and get a certainty of plus or minus 0.0001, I'm not just going to report 45. I need to reflect the amount of precision, the amount of certainty that is in the device that I use. If I look at trailing zeros that happen before a decimal point, those are always going to be significant. And this is the key, that it's before a decimal point and after a non-zero number. So here I have those zeros, but then I have significant zeros because they're made significant because of the decimal point. Here I have non-digit or non-zero digits, so those are automatically significant. Those would fall under that captive zero rule. But here I want to reflect that my uncertainty is plus or minus 0.01, right? So this 0 in that 140.00 is also considered to be significant because my uncertainty isn't there, it's in the last digit that I report. If trailing zeros are before an implied decimal point, they are ambiguous. I want to avoid this situation. I don't know what this means. Is it plus or minus 100? Is it plus or minus 10? Is it plus or minus 1? I don't know from reporting 1200. If I do it this way, I know I have 1, 2, 0, 0. There's two significant figures. This is plus or minus 100. If I do it this way with 1.20, I have three significant figures, which means I am plus or minus 10. If I do it this way, I have four significant figures, excuse me, which means that is plus or minus 1. If I add a decimal point after the trailing zero, anything before it is going to be significant. So this is equal to 1.200 times 10 to the third, because it has four sig figs, just like this one has four sig figs. So that zero, or that decimal place, forces those zeros that are trailing to be significant. Exact numbers have an unlimited number of significant figures. This is going to be counting. I have 5 pencils. I have $10, right? Any integer number that's part of an equation, if I multiply by 2 or divide by 2, right, that 2 has an unlimited number of significant figures because it's just an exact number. Define quantities. So definitions within a unit system. If I go 1,000 grams is equal to 1 kilogram, this is a definition, and this has unlimited sig figs. Now, some conversion factors are defined quantities while others are not. If I go from English to metric, one of those has to be measured and one will be defined. It depends on what conversion factor I'm actually using. So let's think about calculations. When I do a calculation and I'm using measured quantities, so maybe I took this measurement in the lab. Any numbers that are given to you in a problem with units are considered to be measured quantities. The results of this calculation must reflect the precision of those measured quantities. I don't want to gain or lose precision during mathematical operations. So I need to follow a series of rules when I do calculations with measured numbers. First of all, when I have a number, sometimes I need to round off, which means I need to drop insignificant digits. I only do this at the end of calculations. This is important. I do this at the end. I only round at the end. I never round before I get to the end. Now, why is this important? Because I'm going on the weakest link principle. The number of significant figures in the final result cannot be greater than that weakest link or the least certain measurement that's used in the calculation. The actual rule depends on the mathematical operation. The thing is, many times we're going to do our calculations in a computer. I put 2 numbers in. I get like 10 or 11 or 12 numbers spit back at me. Well, this is where I have to round off. I have to figure out how many significant figures I need to report. How many of those digits are actually meaningful based on the precision of those measurements, the certainty in those measurements. And then, depending on the mathematical operation, I report what I need to report, which means I have to round off. But I only round at the very end. I am not going to round in intermediate steps if I have multiple mathematical operations to perform, because that will just increase the error in my calculation. So let's look at multiplication and division. The result, the answer, is going to have the same number of significant figures as the factor with the fewest significant figures. So if I'm going to do 1.052 times 12.504 times 0.53, I have 4 significant figures times 5 significant figures times 2. Remember, this leading 0 is not significant. Well, the factor that has the fewest is this guy, because I have 2 sig figs. So I'm going to do the calculation, and this is what I get in my calculator. Well, now I have to round to 2 significant figures. So I'm going to use my rounding rules and look at this number. That number is less than 5, so I stay the same. And I'm going to report this calculation as, or the final result is 6.7. This works for division as well. Here I have 5 significant figures. These are captive zeros. Those are captured zeros, so they are going to be significant. This is a 0 after the decimal place, so that's also significant. So I have 5 sig figs versus 3. I need to report 3. This is what I get in my calculator. If I look at 1, 2, 3, I'm going to use this 0 to round. Because it's less than 5, it's going to stay 0.626. When I add and subtract, it's a little bit different. What I actually have to do is line all of my numbers in a row and line up the decimal places. See these decimal places? These decimal places have to be lined up, right? And then the answer is going to carry the same number of decimal places as the quantity that I'm adding or subtracting that has the fewest. So if I look at this adding, I've got 3 after the decimal place. I've got 2 after the decimal place. I've got 4 after the decimal place. So if I sort of draw this line here, I want to get to that point. I want to get to, my answer is going to have 2 after the decimal place. That's because of this number here. So I do the entire addition, but now I have to round to this position. Because this is a 2, this is going to round down, and I'm going to stay the same. 5.41 is my answer. Here, 5.9, 1 after the decimal place, 3 after the decimal place. So I'm going to round to 1 after. Here, notice it doesn't affect what comes before the decimal place, it's what comes after. So this doesn't give me 1 sig fig, it gives me 1 digit after the decimal. So here, my answer is going to be rounded based on the 7, and it's going to go up to, 5.6 is going to go to 5.7 because of rounding rules. It's always helpful to draw a line next to the number with the fewest decimal places. This is going to help us determine that. So let's just go over the rules for rounding. You round down if the digit dropped is 4 or less. You round up if the digit dropped is 5 or more. So if I look at that, if I want to round this to 2 significant figures, this is a 7, it's greater than 5. I go from 5.3 to 5.4. If I want to round to 2, this is a 4, it's less than 5, it stays the same. This is a 5, I round up, I get 5.4. Notice I only care about this digit. I do not care about that 9. right? That does not make a difference. I'm just looking at this digit that's next to the one I want to round to. So this is going to stay the same, and I end up with 5.3. Only the leftmost digit that is dropped determines the direction to round. Ignore all the other digits that are in that measurement. Now, when I have calculations that involve multiple steps, I actually have to consider what's going on in a little bit more depth, right? So when I determine the number of sig figs, I have to perform the individual operations. And then I have to decide how many sig figs that individual result is going to have in order to figure out what happens at the end. So if I do this calculation here, I have a subtraction that's going to happen first according to orders of operation, and then I'm going to divide. In my calculator, I get this long number. The first step is doing a subtraction, right? How many significant figures is this going to generate? Well, I have 2 after the decimal, I have 3 after the decimal, so I need 2 after the decimal. This is the reported answer to that addition. This is where the significance starts. But I use this whole number when I do the division because I do not round at this stage. I round later. So remember, this whole piece is giving me 2 sig figs. This is giving me 1, 2, 3, 4, 5 sig figs. So I need to round to 2. This is less than 5. So my answer is 1.9 grams per centimeter cubed. When I have mixed orders of operations, when I have addition and subtraction, and I have multiplication and division, you always do the addition subtraction first, and don't be fooled. You cannot easily predict the number of significant figures unless I line things up and look at the decimal places. Just because there are 2 after does not mean my answer is going to have 2 significant figures, because I don't know about what's going to happen when what comes before the decimal place. So pay special attention to that. So I'm going to avoid rounding errors when I do multi-step by rounding only in the final answer. I'm not going to round intermediate steps. If I write down those intermediate answers, you want to keep track of the significant figures. So for example, here I have 3 after the decimal place. Here I have 2 after, right? My answer to that subtraction is this. My answer is only going to be till 2 after, which means my total for that factor is going to be 2 significant figures, not 3, right? So now I have 3 sig figs times 4 sig figs times 2 sig figs. So when I get the answer in my calculator, I have to round to 2 sig figs. I can keep track of this by underlining the significant figure as I carry them through in the calculation. Now, here's another thing. We've talked a lot about precision, but what does that actually mean? Accuracy and precision go hand in hand when I'm doing or making measurements in the laboratory. Accuracy is the agreement between measured values and the accepted or true value. So if I have a dartboard and my accepted value is smack dab in the middle, the closer I am to that middle value, the closer I am to the accepted or the true value, the more accurate I'm going to be. Precision is the agreement among repeated measurements. So on this dartboard, these guys here, they're on top of each other. There is very high agreement in those particular measurements, but they're pretty far away from the bullseye. So in this case, this is precise, but not accurate. These guys are accurate. Here, I have kind of my darts are all over the place. So this is imprecise and inaccurate because my measurements don't really agree with each other. The precision here is not as great as when they're on top of each other. So I would probably consider that just to be accurate. So how am I going to see this in a lab situation? When I consider the results of 3 students who repeatedly weighed a lead block, and I know that the true mass is 100 grams, okay? So I have a lead block. I know it's supposed to be 10.00 grams. Let's say it's a standard mass. What I'm going to do is I'm going to measure it 4 times. I'm going to take 4 different trials. So I'm going to use a balance, the same balance. Student A is going to measure it 4 times and then take the average of those measurements, which is measurement 1 plus 2 plus 3 plus 4 divided by 4. Student B is also going to take 4 measurements. Student C is also going to take 4 measurements. Here's their averages. Remember, the true value is 10.00 grams. So let's graph this, right? Here is the true mass, and this red dotted line is the average. So I notice in student A, I have a lot of scatter. I'm up, I'm down, I'm up a little bit. These are inaccurate and imprecise results. They don't really agree with the true value of 10.00. And the individual measurements are all over the place, so they're imprecise. Here, I have high precision. My accuracy is off though. So this would be inaccurate because this number is fairly far away from 10.00. And I don't really have precision, or I do have precision because these numbers, though that data is tight, they're very, very close to each other. So this indicates that there's something wrong with my device because I'm measuring it correctly. I'm getting very close results, but they're just not the right results. And then here's what you want to strive for. Here I have accuracy and precision. My average is very close to the known value of 10.00. Remember, in this balance, I'm going to get plus or minus 0.01. So if my thing is 10.00, that's within my the uncertainty of the device. But I also know that my 4 trials are really close to each other. There's not a lot of scatter there. They're very precise. So this is what you want to strive to be in the lab. Now, the results of student A, which are both inaccurate and imprecise, this indicates random error. A random error is an error that has the equal probability of being too high or too low. The results of student B are precise. They're very close to one another, but they're not very accurate. This is indicative of systemic error, which is an error that tends towards being either too high or too low. So there's something that's wrong with the device. The device might be calibrated wrong. It's calibrated so that when you measure it, it's always off in a low direction by the same amount, right? That would be systematic error. Student C is giving me little systematic or random error. Those results are both accurate and precise. Okay, at this point, I'm going to stop because the next topic, which is solving chemical problems, is going to take a little some time. So there will be 3 lectures for Module 1 instead of the 2 that I showed. So I'll be back. I'll be back. Stay tuned.